So good afternoon, good morning, and good evening. Welcome to EIG's 26th webinar, Image to Insight with Fuse Machines and Data Speckle. Thank you for joining us. We appreciate you taking the time to join us, especially in light of the continued coronavirus pandemic. Hopefully your family are healthy and safe. This is the 26th webinar that we've provided. We started about in March. Our focus on building, evolving, resilient enterprise. For this webinar series, our first one was on February 9th, and it focused on document automation, how to, 3 simple steps. And it focused mainly on optical character recognition. Today's webinar, Image to Insight, we're focused on providing practical artificial intelligence for business solutions. And we are focusing in the area of deep learning and computer vision. And we have a case study with the Altman Z-score. We look forward to an interactive webinar with all your comments and questions. Please feel free to ask at any time in the webinar in the Q&A chat window. In the chat window, you'll see the instructions on polev.com/Jim DeVries 073 to log in. Please feel free to log into the webinar or into the Pole EV so that you can vote on the polling. Again, my name is Jim DeVries, founder and president of Enhance International Group. EIG is a platform of 40+ consultants, consulting companies, and SaaS providers. And we really are focused on empowering your organization's workforce to expand and sustain your organization to become a resilient enterprise. Our goal is to provide collective, collaborative, experienced thought leadership to enable your organization to deliver self-sustaining, positive margin growth. And we also focused on providing you 90-day action plans. And so you'll see that in many of our webinars. We thrive on bringing together our consulting and SaaS provider teams to give you the 1 + 1 + 1 = infinity. We do hope that you find this information informative that we cover today. It will become placed on our website, consultingeig.com, under the webinars, and you'll see the 25 webinars that have been posted thus far. And again, if you have a cell phone or can open up another browser window to join the polev.com, we'd appreciate it, polev.com/Jim DeVries 073. Since March of 2020, we've been providing webinars covering the 4 areas that we focus on: people, process, data, and technology. Today, we're in the technology area and supporting building the visible, resilient enterprise digital ecosystem. We've had a few fireside chats, and we'll be resuming those shortly. Upcoming webinars in a couple of weeks is new product introduction and development, speed of resiliency series. And it'll be the 3rd one in that series, and it'll be focusing on digitization tools. And then the following week, we will have 2 webinars, one on supply chain risk and resiliency, and another one on the digital twin. And then the following week, we'll be back here at the end of April and resume this series on the OCR documentation of the human behavior. And then we'll be focusing thereafter on continuing these different series. So with that, I just want to introduce our 2 esteemed guests, C. Bonovich and Dr. Bulent Unaker. I'm sorry, Bulent, one of these days.
That's great.
Bulent Unaker. And C will kick us off with an introduction.
Thank you, Jim. Good day. I'm C. Bonovich, VP of Partnerships at Fuse Machines. I joined Fuse Machines almost 6 years ago after a career in finance. Fuse Machines is an AI talent consulting and education company. We have more than 170 learning, deep learning trained engineers. In addition, we have a dozen senior AI researchers, including Boulant, my co-host. Our social mission is to democratize AI. What that means to us is we've been working with colleges and universities in developing countries to train young engineers in advanced AI skills, including machine learning, deep learning, computer vision, and natural language processing. This year, we are also beginning to offer at no charge workshops in the US to disadvantaged communities. The goal is to expose high schoolers and middle schoolers to AI and to help them imagine a dream in AI as a profession. Thank you. Boulant, want to continue?
Thank you very much, This is Bülent Uyanıkar. I'm a physicist, and I'm with Data Speckle. Actually, I'm the founder of Data Speckle, and Data Speckle is an answer to artificial intelligence. Some time ago, we decided with a couple of PhD researchers, we decided that there should be an answer for artificial intelligence, and our answer is real human intelligence. Maybe human intelligence can help artificial intelligence in some ways. So I'm a physicist. I have started my career as a magnetic field researcher. I have worked with many of the leading radio antennas, including atmospheric and some others. For magnetic field mapping, I have joined space missions for X-ray imaging, and I had the privilege of writing algorithms and contributing cancer research at the Cancer Research Center in British Columbia. And I had the opportunity to teach medical physics, medical imaging, and computer vision courses at the University of British Columbia. We're working together with Fuse Machines and several other partners, and I'm so happy that I am able to contribute to the Fuse AI School in Kathmandu as well for the curriculum, as well as daily research activities and solving real-life problems of our customers, especially in North America. Many topics that we go are including time series analysis, but mostly heavy computer vision, deep learning, and machine learning algorithms. We have worked for companies for underwater imaging. We have worked for companies for object localization and object detection. We have worked for companies for document automation, as well as deep learning applications. Well, in that, I would like to thank Jim and Carol for organizing these wonderful series of webinars. It's been a big pleasure for me to be able to work with them, to be able to contribute to these series of webinars. And to the audience, thank you very much for joining us. I hope it will be an entertaining webinar for you. We will try to make it as simple as possible and as entertaining as possible. Thank you very much.
Thanks, Boulant. Thanks, Boulant. Thanks, C. Appreciate it. So we're going to get started. The agenda today is we're going to kick it off by digitizing documents. It's a recap of what we covered at the last webinar. And then we're getting to machine learning and deep learning, and of course, computer vision, the hot topics of today. And then we're discuss extracting information within images. How do we do that? And then we have our Altman Z case study, followed by Fuse Machines AIDR Framework, and then Q&A. Again, if you have questions throughout the webinar, please enter them into the Q&A, and we'll do our best to answer those as we come upon them. With that, C?
Sure. As Jim reminded us, our first webinar was on OCR, and which is the first step to digital transformation. And if anybody is interested in listening to that, please just reach out to one of us and or go to the website. Today's webinar is Image to Insight, and we are trying to give you some real-world practical solutions to how to use AI in your office. And then our third webinar in the series, which will be April 20th, will cover documentation of human behavior, both from the visual and audio worlds.
What?
All right. So this is, if you have attended our first webinar, this is our general workflow for document automation. Basically, we have several issues. Digital data or information comes from all over the world from different channels. And the first raw material, so to say, is the digital data itself. That simply means if your data is already in digital format, if you are simply getting your information from an email or website or a document which is in Word format, a freely accessible digital data. When we have freely accessible digital data, then it is already in the format of ones and zeros, as we have discussed last time. And with that, it is possible to use and employ any possible algorithms to extract the information. So basically, if we have the digital data exist, then we simply employ many methods of machine learning as well as deep learning to extract information, because at the end of the day, our aim is to convert that information into wisdom. In this chart, from left to right, we see the increased cost and time, because the next step is usually when we do not have digital data exist. That simply means that the information is around, but it is embedded in something. It is embedded in a document, it's embedded in an image, or it is somewhere hidden, we need to find it. So the second step usually involves converting those images, those information in documents into digital format, then afterwards continue with our regular processing. This step usually involves OCR, the optical character recognition, that partially involves computer vision as well as some machine learning techniques nowadays. But if you remember from the first webinar, its origin goes back to very simple computer vision ideas. When we simply move on further, we see that there are other things happening, because if you do not have data, digital data exist, and if optical character recognition is not enough, then it must be somehow augmented with computer vision algorithms. Because although OCR is inherently a computer vision algorithm, it is not designed for any specific purpose. It is able to extract information. It is trying to convert the letters one by one and then combining them, trying to build words and further sentences and try to find the layout. However, it is not designed for any particular purpose, because the logic behind it does not know whether the algorithm is tackling with an invoice or a receipt or a legal document. Again, in this particular step, in step 3, we simply enhance OCR applications using computer vision. In that way, we employ pattern recognition and probabilistic approaches come into the play, and then we simply reach to our ones and zeros again and continue. The other problem, however, is most of the time we do not know where the information that we are seeking is hidden. For that, actually, we have an answer. We come up with deep learning. Suppose that you are looking for a particular information, a table, a receipt, or just one simple excerpt from a legal document from a given book, which is 1,000 pages, or so many books. Suppose that you have a library of books and you are trying to extract some information. In that, machine learning and computer vision alone is not going to help us because we do not know where the information to extract. Then we employ deep learning algorithms. Basically, we simply make the analogy: seeking the needle in the haystack is the task of deep learning. We simply train algorithms, give hints and clues about the information, the object, the table, or whatever we are looking for to the algorithm. The algorithm starts identifying, learning each different versions and variety of those objects it's looking for. Then afterwards, it simply seeks through all these vast amount of information and finds the tables or whatever the information we are looking for. And then the task is delegated to computer vision and machine learning algorithms. Moving further, if we would like to summarize the whole, we simply try to extract information, convert them into the digital format, then afterwards process them using data mining techniques, processing, natural language processing, and there is a lot of other possibilities exist once we have the data in digital format. The several ways of just getting the information we have just listed here. We can scan the documents. Sometimes because we don't have the digital information already, we receive them through emails, we receive them through documents, and what we usually do is we convert them into images, PDFs, JPEGs. We pre-process them, we analyze the documents, we extract information we are looking for. We usually employ character recognition, and then afterwards we post-process and extract information. This kind of documents usually are images, photographs, it could be video, it could be signs, traffic signs, billboards, it could be any type of information, including handwritten or printed information. Here's a little, moving forward, a little sketch which OCR relies on. OCR has a predefined idea of an object or a letter, how it should look like. It comes with a prototype, and using that prototype, we try to see the object that we are trying to classify. We try to resemble that object to a prototype that we have, and we match it. And this is the way the OCR usually works. Moving forward, we have actually one example of how OCR and combined algorithms work. In this usually is the step 2 and 3. Mostly we call this step 2 when we simply look for any information where we do not have digital data exist, but we can simply OCR, extract the information, the characters one by one, combine them, and extract the information or the wisdom that we are trying to reach that. An example of that is in the next slide that is simply showing us one receipt. These receipts can come up in a very different ways. The quality maybe most of the time are not adequate. When we scan them, the orientation usually is tilted. Here we are showing you one deliberately. The image is tilted. The quality is probably not that good as a PDF image, but the idea is we would like to reach some, we would like to get some information from this. Most of the time in these basic applications, we would like to get the address or the total purchase amount or something else, maybe the receipt number or the time and date, if we are interested in the time analysis. The regular OCR augmented with post-processing NLP here gives us the results by simply detecting individual characters and combining them into words. We see the words are identified in green boxes here in that image. Obviously, the original image is, the orientation is corrected. That red box around showing simply the orientation correction. And obviously there are some other image processing, denoising, and trying to make the effect of background smaller, and such pre-processing steps involves that. This is one way of simply using OCR and computer vision augmentation. One single receipt obviously is not going to tell us much, but considering that you have thousands of them, and it doesn't have to be receipts only, of course, then we need some sort of an automation. In such an automation case, computer vision and post-processing with natural language processing is the ideal tool. Then we do not really need to go very extensive and expensive machine learning or deep learning solutions for this purpose. Moving forward, we simply are going to concentrate on more the machine learning and the computer vision techniques in detail. And we would like to give you an idea of what do we mean when we say computer vision and when we say deep learning and machine learning. If we simply start thinking about what is a vision, what is a computer vision, we can come up with many different definitions. But the simplest definition I find is it is simply mimicking the human vision. Mimicking human vision starts actually, probably goes back to 300 BC, because in the old texts of Aristotelian texts, they are talking about pinhole cameras. So here is a pinhole camera. It's basically a lensless, simple box. And the discovery here is if you have a box and if you have a hole, then you can actually obtain an image, an inverted image of the object at the back of that box. That box, or that surface of that box, we usually call as the image plane. And the discovery here is very important because they have discovered, this happened around 19th century, they discovered that the diameter of that hole that we are just opening in that box is actually very much important, and that is very much dependent on the length of that box from the hole to the backside to the image plane, and that determines basically that distance is the focal length if you are familiar with photography. And that focal length, that diameter of the hole determines how sharp you can get your object. Nowadays, we don't use these pinhole cameras, but the principle is the same. Instead of that hole, we usually have a lens, and instead of the plain box, we usually have a film or a CCD chip at the back, a sensor, which simply collects and gathers the light. Okay, so once we understand what computer vision is, we can simply move forward and see what computer vision can do for us.
Just 1 second, Bulan. We want to recognize Scratch a Pixel for allowing us to use their image.
Oh, thank you very much, Jim. I almost forgot that. Yes, Scratch a Pixel is an educational website, and we are really thankful for them to provide us this slide, this drawing over here, just showing us the pinhole camera. Thank you very much, Jim. So once we have that image, once we have that film or just CCD sensor at the back, now we have a two-dimensional numbers, basically. Now I'm skipping directly to the digital part because we don't want to spend much time on the analog part. But on the analog part, you can see this beautiful image of the standard testing image of Lena. We can see that there is a very important thing that is happening in this image, which is actually the brightness. So when we look for any image, we can identify 4 characteristics of a typical digital image. The first one is the matrix. First one is the size, the rectangular array of numbers or expressions that is defining the area. And the second thing is the pixel. That is the individual matrix boxes. Each pixel contains a number of discrete value that is representing the brightness value. And if you're familiar with the field of view concept, you can simply figure that your field of view is actually your pixel size times the area of that whole big matrix. And the third information that we get usually from digitized images is the information contained in a volume. That simply means that we can have layers of information like a CT image that simply provides us different layers of information from a given image. And the fourth important parameter of a digital image is the bit depth. That is basically the number of bits, the binary digits given in that pixel. Along with these four parameters, we can identify the whole characteristics of a given digital image. Here we see on the left and on the right-hand side, the changes in the brightness when we simply play, if we simply redistribute the brightness in that given image, we can simply change the brightness and the appearance of that image. This is basically one of the prime examples of computer vision. Everything in this image that we see, segmentation, brightness, or just the distribution of the brightness, all these manipulations and operations are the elements of computer vision, and everything we see today in medical imaging and many areas simply rely on that information, on these processes and development in computer vision. Moving forward, we do see some other enhancements. This is the next step. We have an object, we have, let's say, our beautiful co-host, Carol, and we would like to recognize the fiducial features, so to say, the facial landmarks. This is the whole idea behind face detection algorithms. What we do is we simply go and by clicking manually on some certain points, the shape of the face, the length of the nose, the width of the eyes and mouth, all these points are marked manually to determine the features. Next time when the algorithm looks at an image, the algorithm will be able to recognize those features again. There are certain other ways of automating this process, but this is one of the prime example of computer vision merging together with machine learning. And this is a very different thing that simply brings us to the notion of what is the difference really between that machine learning part and deep learning. We are still not talking about deep learning here. We are still talking about computer vision and machine learning algorithms. If you really ask me what is the difference between machine learning and computer vision, we have a slide that we are going to come to that, but basically we will see that there is going to be so many different layers. We will simply talk about this. This is computer vision. We passed it. Now this one is the deep learning part. In the deep learning part, in contrast to the previous image, going and finding those landmarks by hand and marking them and feeding them into an algorithm, we have a different approach here. In this approach, on the left-hand side, let's say we have a stack of images. They could be cars or something else, a truck or van, or even a bicycle or a dog. What we do in this approach is we simply identify little areas from those images. Those little areas all by themselves do not really mean much when we look at them and inspect them visually. However, all this information, all these little features carry some specific information regarding some part of that image. It could be the color, it could be the curvature, it could be any property that comes with the image. If we simply have all these stacks and extract those regions and feed them into layers, we usually use the technique of the convolution, hence the name the convolutional neural networks. The idea behind neural networks is obviously there is synapses, and the idea is totally stolen from the human brain. It's not exactly replicating it, but it's some sort of an activation function idea. There is a function. That function simply works like an on and off switch, and based on the information enters into that function, the activation function. In this case, we see the ReLU over there, which is the short for rectified linear unit, is a piecewise linear function that simply output the input directly if the input is positive. Otherwise, it's simply outputting the outputting 0. Basically, the node is not activated, in a way mimicking the synapses in the brain. Convolution is simple multiplication of large areas with small areas, and we are trying to reduce the information from the whole image at the same time, and we are trying to reduce the size, and we are trying to extract most important information from the given image. When we move one step further, in that box, we see those little areas like pyramids. We simply take a little sample from those images. Remember that these boxes are stack of images. Those little parts of images go into a pooling session. Pooling here means we would like to eliminate information, and we would like to get most important information. We would like to extract most important information from the image by eliminating many features that are not going to be useful for us. That simply reduces the amount of parameters, and is all at the same time reduces the amount of computation. Usually max pooling, you simply look for an area, get the maximum values in that area, and just pass it to the next layer. So when we see all these boxes, we're talking about layers. So at the same time, we're learning the jargon of deep learning here. So we have an activation function, we have rectified linear unit, and we do pooling to extract only the important information. At each level, as you see, we are extracting specific information. Then what we usually do is depending on the complexity of the algorithm, we repeat that process, convoluting further and activating and pooling and so on. In the last layer, we simply flatten the information. That is to say, all this information coming from 3D, we simply convert that into a one-dimensional array to pass it to the next layer. Because any two-dimensional image and any convolutional layer usually outputs a three-dimensional tensor, which is usually scaling with the resolution of the image and the number of filters we are using. At the end, we need to pass that information for decision-making. Here we are marking this as classification part, because the end layers of any neural network is a classification layer. That flattened one-dimensional array then simply passed to the last stage for the classifier, which we usually call as fully connected layer. Sometimes we call it the dense layer. That is actually the layer we use for the classification purposes, because any classifier needs individual features. This means any classification layer requires a vector. Hence, we need that flattening and fully connected layer. And afterwards comes the softmax part. Softmax is just another name for an activation function, which is the output layer. Its task is actually predicting the multinomial probability distribution and make a decision on whether the input object is a bicycle or a van or a truck or a car. I hope this gives a good understanding of what we mean with deep learning. We can just move one step, and I can actually tell you what I think about the difference between machine learning and the deep learning. One thing I just forgot to mention here in that image of, dog and then a bicycle, we see all these little squares. All these little squares correspond to these little pyramids or that extracted portions of those images in the above boxes. Okay, moving forward, let's just make the distinction between machine learning and the deep learning. There are so many definitions of that, but practically, I find two factors are determining the difference between machine learning and deep learning. Basically, they both are the subset of the artificial intelligence algorithms, which can simply modify itself without human intervention by feeding itself through the structured data. In a way, they both do the same task. However, in deep learning part, there are numerous layers. That is the first and very important distinction of deep learning as opposed to machine learning. So in deep learning, we have numerous layers. Each algorithm can provide a different interpretation of a different layer of a different data. In a way, we have some hierarchy of layers defining specific features in deep learning. And secondly, in deep learning, we do not need to use structured data all the time. And the other distinction of deep learning is deep learning extracts features itself. So basically, my definition of the difference between machine learning and deep learning is in deep learning, we have multiple layers and a hierarchy of information. And in deep learning, we can extract features using the techniques that we have discussed just a minute ago, whereas in machine learning, we do not necessarily do that. So if we look at the first drawing at the top, we have car images. We extract manually the information. We simply feed that information, like the facial features, that information into a classifier, and we simply so that machine learning box is where the actual magic happens, and we determine whether that object is a car, a truck, or so on. In deep learning, we don't have that manual feature extraction part. That feature extraction part is happening through those layers, and a probabilistic output is giving us the classification result. But in a way, both are going to be identifying whether that object is a car or a truck or a bicycle, but using a totally different paradigm, totally different approach. So this is my 2 points of determining whether an algorithm is a machine learning algorithm or a deep learning algorithm.
So, Roland, just as a quick question here. So is machine learning more decision-based with a set of decisions, and deep learning is more looking at the features and then looking at the probability of that meeting certain criteria?
In both cases, in machine learning as well as in deep learning, the approach is gaining the set of rules determining the output from the data. This is the huge difference between machine learning, deep learning, and in general AI algorithms with the traditional statistical algorithms. Because in the traditional statistical or even probabilistic algorithms, what we have is we have an understanding of the process. We know how the process is going to take shape. We simply feed in the data based on our perception of the solution. We try to find the solution. Whereas in both machine learning and deep learning algorithms, we do have the solution, we do have the problem, and we don't know what the process is. And we usually find that process through machine learning and deep learning algorithms. The association is, so to say, the discovering the association of that process or the variables. I hope that answers your question.
Yep, perfect. Thank you.
All right. So again, we have used some examples of dogs and bicycles and cars, and this actually brings us to a very interesting thing. But one thing we need to keep in mind all the time: these algorithms do not know what they are doing. they're not self-aware. Unfortunately, AI is not at that stage yet. They simply employ all these mathematical functions, activation functions and convolution, all these complex functions, whatever we simply provide them to. If we provide flowers, they simply apply those algorithms to flowers. If we simply feed the cars or traffic signs into a deep learning or a machine learning algorithm, the algorithm will start getting bits of information, collecting all that little grift associations one by one from vast amount of information, then tries to combine them. But at the end of the day, it doesn't matter whether it's a car or a flower or a dog. However, we also need to remember that the algorithm will only function for the model, for the data it is trained for. In our case, for business purposes, obviously, we would like to feed business information, invoices, legal documents, any kind of document, any kind of information written on the signs, license plates, or your passport information, anything possible, including facial features. All this information may have business values, and we are going to be mostly concentrating on these parts in the following slides.
To our second polling question. See?
Yes, absolutely. How comfortable are you in having computer vision used to track people's activities? Are you very comfortable? You just think it makes it easier and more secure? That's A. You're comfortable, you think it's necessary, but you don't like it. Or C, that's B. C, so-so, I am somewhat uncomfortable. And D, I try to avoid it whenever possible. It reminds me of Big Brother. Why don't we spend a minute answering that question?
So thanks for responding.
We also had a question, and I don't know whether we should wait till the end or we had a question, and I could answer it.
Why don't we answer that? Go ahead.
Okay, the person is asking what we think the impact to shift workers will be from machine learning, deep learning, and all of this. And my answer is there will be an impact, and there's certain jobs that can be done better by robots, better by these new technologies. But there will be the elimination of certain jobs, but there'll be many more jobs created. So it is not a zero-sum game in the sense that if there's just elimination. So there will be both elimination and addition. I hope that answers your question.
It's a great comment. It's one of the perplexing questions is how is the day in the life going to change in the future?
Mm-hmm.
And
so
it really comes down to repetitive. I look at it from a repetitive task perspective versus add. So I think people will be doing more valuable added actions
higher
at
functioning
the workplace and higher functioning. And when you look at from a lean perspective, and 80% of the work is non-value added, at least a lot of that we're not doing, or we're waiting for it to accumulate, and so things aren't getting done. So just to make it clear, in the workplace, there's a lot of things that aren't getting done that if they were getting done, it would make the workplace a much better place.
Correct. So 77% of people are so-so or comfortable. So the overwhelming majority are okay with it. And then we have 22% that are very comfortable. And nobody in this group found it too creepy. So that's good. That's good.
So we don't have to go back to 1984. We're not there. That's good.
Okay.
Of course, that book has changed everything because everybody is worried about that. Great. Thanks everyone for participating in the poll. Very interesting discussion. With that, just to talk a little bit from a high level of continuous data and process mining environment. You know, it's one of the most significant challenges that we have in developing a meaningful digital data transformation for a company. You know, our overall goal is to take as much of our day-to-day interactions into meaningful ones and zeros so that, you know, analysis can be performed to support informed decisions, just what we were just discussing. You know, traditionally ERPs are out there set up to collect prescribed data to support really from an accounting perspective in the beginning, and then kind of enhanced its way through to more of the workflow processes over time. However, the actual data, the day in the life of the employee has been kind of left out there. And what we're seeing is with this new digital revolution through social media, emails, text, the day in the life of the person is now being able to be captured into ones and zeros. And as Boulant shared with us, we can start placing machine learning algorithm on them. We can start making the work environment a much friendlier and easier place for the user, less stressful, so that we can get to that end of real-time computer vision and deep learning environment. And, you know, ethnography, you may hear of video capture, pattern recognition are some of the things that we'll be seeing in the future. So, you know, as we mine the data, again, through all these different places, from a numerical business information, newspapers, or online chat rooms, competitor promotions, customer messaging, even interviews of any type, and then being able to harvest those into the area of focus, or area of interest, and then using everything from web scraping and natural language processing, we're going to see a lot of changes in the work environment to make it a much better place to work in. And when you look at it from a CEO perspective, you know, the CEO is definitely pressured to make decisions, make informed decisions based on data, but we're still not at that place where the CEO can rely on the data around them because it's lagging, it's not real time. So what we're going to see in the next 3 to 5 years is a significant change there, where the C-suite will be getting real-time data so that more informed decisions can be made. See?
The AIDR Framework is a framework that was developed by Fuse Machines CEO, Samir Maski, who is a professor at Columbia University. And we use it as a way to think about a problem and to figure out if this problem makes sense for an AI solution. So first of all, we have to find out if there are algorithms that will help with this problem. And typically we're using open source algorithms and customizing them. And today there are lots and lots of algorithms to choose among. So that's number one, algorithm feasibility. Number two for us is impact. Solving a problem with AI takes time and energy and therefore money. And so you don't want to focus on a problem that won't have a significant impact on your business. And typically you want the impact to either generate additional revenue or reduce expenses, something really meaningful for your business. Third, do you have the data? There's no AI without data. I mean, I think you've gotten that message from what Boulant was sharing today, that data is key and data is king. So do we have the data? Can we, or if we don't have it, can we acquire it? But that is the the holy grail when it comes to AI. And lastly, is this a recurring issue? Is there recurrence? Because ideally, when you're solving with AI, your problem or your, I should say, I don't want to call it your problem, but the system is collecting more and more data all the time. And then that data is going to be fed into your algorithm, and you are going to be getting better, more accurate results continuously. And that's the beauty of AI. It's looking forward, not backward. If you have any specific questions, you can put them in the chat, and we can answer them at the end of the webinar, or you can just reach out to me. Thanks.
Thanks. And if you, are there any questions in there that we can answer right now, see, in the chat room? If not, we'll just move on. And just a reminder to everyone, it's 7 minutes to the hour, and we'll probably end up going a little bit over. We're going to be talking about applications in this segment. But if you have any questions, please enter them in and we'll answer them right now if we can. And she said, we'll answer them after the webinar if necessary. So with that, the example that we have is the Altman Z-score. And this is a very common financial indication of a company's ability to perform well, especially from a bankruptcy perspective. So they say Altman Z is going to help you understand how well a company's operating. Is generally used in the supply chain world of evaluating their vendors. And so the challenge is how do you calculate this Altman Z score when quite a bit of that data is in financial documents? It may not be available digitally, and it's a challenge to really transform that key data into business analytics. Of course, Altman Z is just one of the many financial health indicators you would want to look at for a supplier or a customer that you're working with to make sure that the customer will pay the bills. So our goal is to automate this process of pulling in all this financial data to tell the story about a company. And the bankruptcy predictor that was developed in the 1960s by Edward Altman, professor of finance at New York University, was used again to predict the probability that a firm will go into bankruptcy within 2 years. It's used to predict corporate defaults and an easy to calculate control measure for financial distress status of companies. So the Z score there is one for manufacturing. There's other constants in front of these different parameters that are out there for private companies, and be wary about using this for a finance company or a company where the balance sheet may not be as straightforward to show this, but it's really built for somebody who's manufacturing. The Altman Z score has a red zone, a yellow zone, and a green zone. Of course, the red zone is when you're below a certain number threshold that was proven by Altman, in this case about 1.8, a yellow zone where there's some risk from 1.8 to 3, and greater than 3. And again, this is just an example of using this process that brought us through these 4 steps of translating a financial statement into ones and zeros so we can calculate that. So Bulon.
All right. For this particular use case, we have used a convolutional neural network model, very similar to the one that I showed you in a couple of slides before. The idea here is we would like to extract as many information as possible from given documents. That includes financial tables, figures, title pages, signature pages, and similar information we would like to extract from the images of financial documents. And we know that there are several thousands of pages available around, and we do not necessarily know where the financial information or where the figure is. For that purpose, we have trained a convolutional neural network algorithm by providing approximately 15,000 examples of figures, images, title pages, and signatures from totally independent documents we simply downloaded from the internet. And we trained the a recurrent neural network algorithm to figure out all these, extract all these information using the technique that I have explained in the other slides. When we simply start running this algorithm on unknown documents that the algorithm has not seen before, we were able to capture some information here. So here in this slide, what we see is the document itself and overlaid green boxes showing the detection of the algorithm. The algorithm identifies on the left-hand side the cover page, the company information, and in the midsection, we see that the algorithm is able to figure out that there is a figure over here, and for the other parts, it is able to figure out the location of the tables. This is very important information because considering that you have tens of thousands of pages, and if you don't know where your information is, where your table is, or where your cover page is, it is very difficult to do this manually. It is possible, but it is very difficult to do this manually. Deep learning algorithm simply goes and finds all these features and figures out with given probability that this is a table, this is a figure, and the rest is, however, again, in the hands of machine learning, text mining, and natural language processing algorithms. What we did here is to identify those features, and we tried to extract financial information from some certain companies. In this example, we did the same thing for Apple and Motorola, and we have also checked the results and compared their accuracy with the Yahoo financial pages to make sure that we are on the right side. But this is just an example, just to show you how this algorithm in principle works. But this algorithm is not devoid of problems as well. Main problems we simply see in this kind of documents is having images embedded in the tables, or having some textual information formatted in a very similar way to a table. On the left-hand side, we see that example. We do have images, pie charts embedded in the text, and the text is very much similar to a table. Obviously, if we train the algorithm differently, we could avoid this. We could simply eliminate all the structures that includes images. That depends on what we would like to do. Would you like to extract the index images? Would you like to extract the information about decision makers? Would you like to extract about information on the financial status? It all just depends on how you're going to be training the algorithm. As you see in the left, we do have some errors as well. The green box is not exactly fitting to that text. However, it should not be actually detecting this at all, because this is not a regular table that we have trained the algorithm for detection. As you see on the right-hand side, it is rightfully figuring out that this is a table, and the lower image obviously is confused with the paragraph on the left-hand side. But again, there is a lot of images in that page. Moving forward, we can see some really good examples of financial documents. And one more thing we need to add here is, of course, once we detect all these algorithms, we are not solely simply going and blindly extracting anything possible. We are aiming for some certain information. Suppose that we have a figure, or we have a table looking like paragraph, which does not contain the financial information or any information that we are looking for, we can easily eliminate them in post-processing, namely in the natural language processing and the machine learning part. Here we see 3 examples of financial documents, and from these similar tables, we have extracted information that are necessary to calculate the Altman Z score for these 2 companies. And from onwards here, we can actually see one interesting slide. The upcoming slide is very interesting because it's displaying us in a different way, both the way the algorithm can fail, and at the same time, it is telling us the opportunity, what we can use these kind of algorithms for. Since we have also included images in the table, the algorithm looks for some certain images and it discovers some tables because there's text involved, or because the structure in that image looks a lot similar to a table. But this is actually a good thing. We can eliminate this. This is the first thing. The second thing is, this is a good thing because if you like to extract the car or a building or anything else, then actually the algorithm can be trained for that purpose, and it can be used for any other purpose as well. This algorithm was for financial information. Obviously, if we get a green box here, it says cars are talking. There's no financial information in that. In post-processing, these are all eliminated. What we are left with is the information relevant for Altman Z. And in the next slide, we are going to be showing how we have used that information, the extracted information, to calculate the Altman Z score. Again, this is just an approximation. Jim, maybe you would like to comment on that.
Yeah, so through Bulant's great work, and he was able to extract the data, and for the last 4 years for Motorola and Apple, and calculate the Altman Z. Please do not read too much into the calculation for these companies, but this is our interpretation. Of course, you would always want to have a professional financial analyst for that company to verify these assumptions on how we're extracting the data. But from our best interpretation, you can start looking at Altman Z calculations and or net sales year over year, quarter over quarter. We just took it at the year basis just to see how the company is running, and is the Altman Z increasing or decreasing over time? Is your revenue increasing? Is your bad debt increasing? All these are different parameters that would help us from the health of a company by using these algorithms. So you could imagine if you had 20 or 30 suppliers and you were able to train the algorithm to extract and automate this every quarter, let's say, update this. And if you see your supplier's Altman Z score going down, you would be able to start asking some questions on how you're going to protect against that, being reliant on that supplier, maybe look for another supplier or do some other things. So again, this is a overview of looking at a random a dozen or so companies, and we hid the names to protect the innocent, so to speak. But we can see that Altman Z is not reliant on your sales. It's reliant on your balance sheet, your P&L. And so you see those orange dots on the right-hand side representing those dozen or so companies. And then you can see calculating the Altman Z consistently over time. You see how each of these companies, Apple and Motorola, are doing. So again, this is for illustration purposes only, but it gives you an idea of what you can do. So with that, C is going to take us through some computer vision applications, and we're anxious to hear about your applications in the following.
Okay, excuse me. We had an excellent question, and I thought we should maybe answer it right now. And this is probably for Boulant. What are the trade-offs in using deep learning versus machine learning in solving practical AI?
The most important thing is probably the cost and the effort, because in many of the deep learning algorithms, we need a lot of data, and that data needs to be annotated. That is still valid for machine learning algorithms, but most of the deep learning algorithms, it takes more time to prepare the data set. It requires more effort and expertise, and at the same time, it is more difficult computationally and more intensive computationally to come up with deep learning models. Apart from that, if anything actually does the job for any particular task, we simply tend, and advice is always to tend to choose the simplest application that does not require elaborate and heavy data annotation. Most of the time, data annotation is the bottleneck. I hope that answers your question.
Great. And let me go through this and then think about an answer to this question. People are now talking about in research a new, I guess, a new paradigm, one-shot learning, which my understanding is requires less data. So maybe you could reflect on that. And after I finish talking about the applications, you might share with people your thoughts on how that might impact this type of question.
Well, that's a very good one. The algorithms are continuously evolving, and more we are getting faster algorithms that rely on less data. And obviously, the most important part here is the domain expertise. Most of the time, what we do is we usually underestimate the importance of domain expertise. That domain expertise usually provides a lot of information about how to process and how to tackle with the data. And that simply shapes the way, the type, and the approach of that algorithm. The algorithm can be quite lean, and one shot actually goes in that direction. Can be quite lean if some information in those really complicated, complex images can be safely ignored. Then you don't have to rely on all these information. You can eliminate them quite easily. Apart from that, computing power is increasing and the algorithms are increasing. And I should remind everyone one more time that deep learning and AI is still at its infancy. We are still trying to come up best ways, and we do not still have algorithms that can write algorithms. We do not still have algorithms, self-aware algorithms. So we're not there yet.
Great. Well, let me just review some of the applications that people are using today and where I would say computer vision is used most actively. So let's talk about finance and banking as being early adapters or adopters. Physical security, of course, and we'll talk more about that in our next webinar. And self-driving cars will be probably the largest user of this when they're all out on the road. But you know, right now we're still in a test case. But I did see. Okay, so I took what I call a weather break from New York and went to Florida for a couple weeks, and I saw self-driving cars in the city of Miami with a big sign on the top, on the sides. This is a test. This is a self-driving car. So it's happening. I mean, it's happening today. And I don't know whether it's 5 years or 15 years, but it will be the biggest use of computer vision, in my opinion. Would you agree, Boulant? I mean, when they're all on the road?
Totally. Not only the cars, I think self-flying airplanes self-flying ambulances and self-running trains are actually really important.
Yeah.
I agree with that, though.
And
Yeah.
trucks, of course, transportation of goods is going to change dramatically.
Yes.
Supply chains will change.
Yes. Now, disease diagnosis is being used today. And Boulant worked on a very important study in British Columbia, identifying, using this for mammography and helping to identify women who might end up with breast cancer or very early on. So extremely important, because in disease, early diagnosis is the key to success. It's being used already in retail. Obviously, yes, we've got computer vision definitely working in industrial manufacturing today and in supply chain. Jim, you want to share a few sentences in that area?
Yeah, in both of those sectors, yeah, Industry 4.0 is definitely having a big impact and bringing in sources of information that were not there before, so that there's more data now to analyze than we've had in the past. Before it was just on off, the machine was on off. But now when you bring in a GoPro camera onto the floor for safety, for the computer vision, you're bringing in to watch how people are working. Are they working in a way that could harm them from a physical perspective? We have partners that are focused in on that. And then just efficiency of the floor are the people doing what you would expect them to do. And it's not a watchdog, it's more of an enablement to help people actually focus on the right task at the right time. The manufacturing floor dramatically increase productivity.
And additionally, I mean, computer vision is being used in marketing, agriculture, law enforcement. I mean, it's widely used already, and it's going to become more and more dominant over the next few years.
Totally agree with that.
So if folks would identify any applications that they are thinking about,
that would be great.
Please,
yeah.
Any ideas that you have? The folks that have hung on way past the hour, we appreciate it. We knew the webinar was a little over the top for 1 hour, but we thought that to tell the story, this is a heady topic. So condensing it down to this size of a webinar was difficult as it was. So welcome folks to enter in where they might find use document automation. Any other ideas out there on where you're seeing computer vision, deep learning, algorithms, any of those application areas on the industrial floor, security, medical? Restaurant servers, there you go. Especially overseas. You know, you go to a country like Japan and they've been working to automate all of this quite a bit, even before COVID. Education. Yeah, facial expressions. You'll see this being used. Are people really understanding what you're saying? And we can see that, you know, these people, you know, you can train your algorithms over time that George or Marlene aren't paying attention or they're not understanding, to help the teacher really on knowing and understanding how their explanation is clear or unclear to the students.
One idea that we're working on right now is having students do self-tests, meaning nobody's been in school, but schools want people to take both yearly exams that some states have, right, for different subjects in different years. And there are certain exams people have to take to graduate. And we have come up with a plagiarism system, really, so that the computer vision is being used to watch the student during their exam. And we will have this available to start demoing to people April, probably, if anyone's interested.
A lot of different ideas out here. Object recognition.
Social distancing.
Bulent, you want to talk about object recognition?
Oh, object recognition is all over. Starting from a grocery store to an airport to any place, even for security purposes, object recognition and object localization is very important. And especially in manufacturing, it's very important, especially thinking about robotic arms doing most of the heavy tasks. Object recognition, pattern recognition are going to be very important when we try to optimize things. Self-driving cars, the same thing, pedestrian detection and the environment detection, and obviously communicating with the infrastructure, because we do have now traffic signs that are really passive traffic signs. It just tells you stop, but it does not inform the authorities if you do not stop. But if we have smart traffic signs that can simply get that information, or any traffic sign showing the speed limit can tell you about what happens during winter time on that particular road, is going to be a very important thing, because that traffic sign can talk to your car and tell that you should not really go fast here because during this time in winter it ices. And all this kind of information currently is not available.
That's it.
Very good.
Thank you.
So I think we're going to wrap up the webinar. Bulent and C, thank you very much. Very educational. We apologize for going over. And thanks for the folks that stuck in. We know it's way over.
We've got one
hope
more
you
question.
informative. And oh, you got a question. Great.
Yeah.
Let's
We've
get
got
it.
2 more questions. One,
Nice.
do you think empathy will reduce when everything is done by machines, like self-driving taxi and restaurants by robots? Jim, do you want to take that, or I'll take it? I don't.
I didn't hear the whole question, so you better take it and I'll chime in.
Okay. Do you think empathy will reduce? I don't know. That's a very interesting thing to reflect on. I'm not sure. I mean, it's not an easy thing to answer. I really would have to think some more, but
Well, there's two theories of thought there. Is one is we'll become more isolated. The other is we'll finally have time to talk to each other and have real conversations. So there's 2 theories of thought, right? One is all the computers will automate everything, so we'll isolate ourselves. The other is, no, when we stop automating and we have more time, we're going to naturally find more. We're social animals. If COVID taught us anything, we're social animals. We need each other. And so I think all this automation really, depending on your society and where you want to live, will depend on, do you want to be an isolationist or do you want to have people around you? But most people want to have people around them and socialize and have more empathy for each other. Hopefully we will move in that direction. But every government, society is different. It's really hard to answer that question.
But I do think COVID, well, we'll have to ask people, but my gut tells me, and I'd be curious to ask people, that it has made more people more empathic, or, you know, having more empathy. But we'll find out. It's a good question.
Very
And
good questions. Very good questions.
the last question is, how many digital marketing tools will be obsolete for digital marketing and replaced by AI digital marketing tools? Well, pretty much they'll all be upgraded. Where you can use AI effectively, you will. So I think the people that have the current marketing tools, I think all know this and will be upgrading them to use AI. What do you think, Boulan?
Yeah.
I think advertising will be drastically changed. We will go more, we are actually on that path already. We will go more targeted marketing, and we do not need to really go for blindly and try to advertise everything. Even billboards will be changing, and I have always this vision when I'm just passing by to a billboard. If the billboard is a smart one, and if it recognizes my license plate, and if the billboard knows that last time I watched that next Netflix movie or just purchased something on Amazon, it can definitely show me whatever I'm interested in. That can text me actually while passing by some information. It can tell, oh, Best Buy, you have the beautiful computers now, just seeing me. And similarly, when I'm walking out of the market, maybe they can just tell me what I need. They can tell me you don't have milk at home. It's not only an invasive technology, it's just making life easier, because I'm going to be buying milk at the end of the day anyways, or a computer.
Right. But yeah, I mean, it's a good thing, and people are figuring out how to use it successfully in advertising. So it's good for the advertisers, and
Great.
decide as consumers, you know, how much we like this micro targeting. I mean, I always laugh about how you get things shown to you that you've already purchased, assuming that you want to buy them again. I want the algorithm to, well, if I bought this red plastic box, I don't need another red plastic box, but I might need some stuff to put in it. Anyhow.
Or,
I think they
or
are
a
very
lid
similar to the pains
to-
that people have experienced at the beginning of industrialization. Suddenly, the ways of producing and manufacturing changes, workforce is changes, and it's very difficult to adapt at the beginning. I think we are having the same type of questions and same type of concerns when technology drastically changes around us.
Definitely.
Great. Okay.
I think
Any other questions coming in?
no, unless somebody else has one. I want to thank everybody for asking questions, and they were very interesting, and
Yeah.
they help us reflect on future webinars. I mean, the question,
Yeah. So I'll just,
personality.
so you got another question?
No. I mean, I'm just reflecting on, will people be have more empathy or less, is a very interesting and somewhat profound kind of question.
Yes. I think that is a big question that people are asking. There'll probably be books on it, on that topic. All right.
Thank you.
Thank you. So I'll wrap up the webinar now, if I can. And there is a summary here. Do you want to quickly cover this, Boulan?
One sentence: choose the simplest solution possible.
Right.
I think that summarizes all.
Yep, perfect. Right, and with that, I just close it out. We do have a webinar in 2 weeks, and it's on new product introduction, and we'll be getting into some of those marketing questions that you just mentioned from a new product introduction perspective, and introducing some digital tools there. And then followed by another webinar on supply chain risk and resiliency, focusing on the risk appetite. And then we'll be focusing on the digital twin. And so with that, Again, thank you all for sticking in here all the way to the end of an hour and a half webinar. Thank you so much.